A ray of light traversing the surface, separating two mediums of different density, is refracted, that is, deviated. But light is composed of various colours, and the angle at which the colours are refracted differs for each of them. For this reason, in a positive lens, the light rays do not all converge exactly at the same point, but the radiations of shorter wavelength focalize closer to the lens and those of longer wavelength further away from it. This phenomenon is known as chromatic aberration. The lack of a single focal point provokes a phenomenon of iridescence, which significantly impairs the quality of the images. Already the first telescope makers had empirically realized that the effects of chromatic aberration in a telescope substantially diminished when the ratio between the focal length and the diameter of the objective was increased. 17th century telescopes, in fact, not only had relatively long focal lengths, but were also usually fitted with a diaphragm to reduce the aperture. But the focal length required to limit the effects of chromatic aberration is not proportional to the diameter of the objective, but to its square. If, for example, an objective with aperture of 2 centimeters shows no appreciable chromatic aberration for focal lengths of at least 75 centimeters, an objective having double the diameter, i.e. 4 centimeters, must have a focal length 4 times greater, or nearly 3 meters. This circumstance profoundly conditioned the subsequent evolution of the telescope. On the one hand, progressive increase in the diameter of the objectives led to the construction of increasingly longer telescopes, to the point of reaching the practical limits of fabrication. On the other, it stimulated the search for solutions based on the utilization of mirrors,